Hello, everybody, and thank you for joining us again for our Citizen Science Monthly webinar series. As you may or may not know, during the fall months, we're focusing on the role AI can play in citizen science and projects throughout the line offices at NOAA. Today, we're very excited to be joined by Dr. Fahim Khan. He is the Assistant Professor in Computer Science and Software Engineering Department at California Polytechnic State University. He received his PhD in Computer Science and Engineering from the University of California, Santa Cruz in 2024, and his research interests include computer graphics, computer vision, applied machine learning, and flow visualization, with recent work focusing on leveraging mobile and AI-driven technologies for real-time environmental hazard detection. We're very honored and excited to have him join us today. And with that, I'm going to turn it over to you, Dr. Khan.
Thank you very much, Rebecca. It's my pleasure to be able to present here. Good morning, everyone, or afternoon, depending on wherever you are. Thank you for being here today. As already introduced, my name is Fahim Khan. I'm an assistant professor in the Computer Science and Software Engineering Department at Cal Poly. So today I'm excited to share about the RipFinder app, which is a project that brings together real-time machine learning technology on smartphone and the power of citizen science, and combining together to improve beach safety, save lives by detecting rip current in real time. That's the technical challenge here. We'll see more about the rip current, and I will mostly talk about the technology behind the RipFinder and how we are engaging the public with citizen science to provide them more guide about rip current and collect more data. So, rip currents are dangerous current that can cause death. So, rip currents are estimated to cause about 100 drowning per year in the US. The observation of rip currents are also needed to support the validation and improvement of NOAA's rip current model, so we can better predict when hazardous rip currents are likely to occur. This is an image from NOAA's website, as you can see, which is very common in various beaches, and some data showing how rip current would look like from a drone view. So there are various types of rip currents. For example, the rip current on the left side is bathymetry rip, which is shown on the poster. We also have flash rip. So flash rips can be detected from the disturbance to the sediment that shows up as discoloration in the water. And we can also have structural rip. So I'm turning off my webcam so that it's not blocking anything important. All right, going back to the slide. So different types of rip currents, as I wanted to introduce. We are mostly going to focus on the bathymetry rips and the flash rips. Structural rips are a little bit different. So usually ML models, they works better so far with bathymetry rips and the flash rips. And then coming back to the technical side, the main idea for rip current detection. So humans can detect rip current based on their experience, which is the usual way of detecting rip currents and the way the lifeguards detect rip currents. So we are trying to think it from different perspective. Can we really use machine learning algorithms, or more known as AI algorithms, to detect rip currents? That can be done in various ways. So main focus here is to detect rip currents based on appearances. Machine learning models are used in computer vision a lot these days to detect objects. One example can be self-driving cars. They use machine learning models to detect object around them, and then based on that, it can drive itself. So, how object detection works with ML model or AI model that is applied in computer vision. So to detect people, we need to train ML model to recognize people. That is done by training the model using a lot of data. In this case, the data is referring to images of people that are carefully annotated to tell the model that these are the objects that we want to detect. For this case, the people. So as you can see, if we have a lot of training data, the ML model can be trained, and then if we have input in the form of visual data, images or videos, it can then detect the same type of object it was trained with. So it is easy for more common objects like people, not that easy for recurrence. So we'll go back to that. There is a close relationship between ML and data collection. So as you can see, there is almost like a cyclic relationship. So data is used for training ML models, and then ML model can be also used for collecting data by recognizing them, and that can be used for other application. For example, rip current detection or driving cars. So how that can be applied for rip current detection? So the idea is the same, like detecting people or driving a car. So we need a lot of labeled images with rip currents. So that's exactly what we did. We collected a lot of training data, which is not quite a lot from the existing sources. That's probably one of the challenges here. Talk a little bit more about that towards the end of the talk. We trained multiple ML models based on multiple technologies. As I mentioned, we are mostly focusing on the appearance based, how it can look like, and depending on that visual signature, we would like to detect recurrence. You can see some example training data here that are collected from various sources. For example, online sources, Google satellite images, and then some of the sources that we have more control over. We'll talk a little bit more about the sources towards the end. So what are the design considerations for the app itself? So when I'm saying app, it is a phone app or smartphone app. So that would run on any iPhones or Android phones. And our goal is to make it work without the dependency on internet or data connection, because practically when we are outside, there is the possibility of not having reliable internet connection. And then the goal is to have real-time rip current detection, which is a challenge because running ML model can take a lot of resources, and doing that on a small smartphone with limited power and processing can be challenging. And then collect and the upload data in a server where we use the data for future research. So that need to be happen, maybe not in the real time, but later at some point when the user has a more consistent internet connection. And then we want to update the ML model and then upload that to the app. So the ML model can be switchable or changeable. The reason is we can see a popular example would be using ChatGPT, where always see newer versions of ML model, which is improved from the last version. So we want to have improved ML model in terms of technology and also trained with more data. So I want to talk about cloud ML versus edge ML. These are more technical terms, but the general idea is the ML model can work in two different ways. One is relying on the processing or compute power of the server, which is not the phone itself. So the phone can communicate with a server, upload the streaming video to a server of something, and the server can detect objects of interest using ML model and send it back. So that would require a very reliable internet connection, which is not always present in the field. And on the other hand, we can have edge computing or client-side machine learning models, where the model is residing in the device itself and also using the available power in the device or the smartphone, which is still a challenge. Smartphones are getting more powerful day by day, so this is getting better, but at the time we started this work, it was not that easy. So, combining all these thoughts, this is a simple flow diagram of the design consideration of the RipFinder app. As you can see, the phone app, it can either rely on the client-side ML model or the local ML models that are running on the phone itself, and using the processing power of the phone, it can generate results and show rip current detection on screen in real time. These are all the requirements. On the other hand, if there is reliable internet connectivity, that can also be used on the app. In that case, the video stream would be uploaded to the server. There will be some delay, but still the processing is possible in the server. The server is obviously much faster. It can process in real time and send the data back. Even with some delay, it can be almost real time. But if that is not available, then the user can always rely on the local ML models. That's our goal here. So the bottom line is both Cloud ML and Edge ML are supported in the RipFinder app. This is just some example. This is not exactly the app on the action, but a quick visualization of how rip current detection would look like if someone is using the phone app. As you can see, when rip currents are detected, it shows the rip current using a bounding box and also this small label showing how much area is covered by the rip current in the viewfinder. And then when there is no rip current, or to be more specific, when no rip currents are detected by the model itself, that can be because it is not trained to detect the rip current, or there is in fact no rip current, you would not see these bounding boxes. There are other options, as you can see. There is a record button and the menu button. We'll talk a little bit more about that. But this is the general user interface. As you can see, the user has the capability of switching ML models. That is, in fact, for advanced user, we have a default setup that would work for the optimal hardware setup for the phone or the smartphone. And then we have other options such as citizen science, data uploading. Ideally, the app works best in this landscape mode. We do have both the portrait and landscape mode. And as you can see, here it is from the landscape mode, and we can have ML assisted photo mode or video mode. So either the user can take pictures and upload that and get some real-time result of rip current detection, or it can be used like a camera where you would point the phone towards the rip current, or to detect if there is a rip current or not, it would show the output based on the ML detection capabilities. Another challenge we considered when designing the RipFinder app is the models are plug and play. So we can see or we hear about various new models every day for all different types of AI application, including the large language models. That also applies to the vision models. Every day, new models are coming. They are better than the last version, and there are different family of models that works differently. We have a small list here. Like when we started this work, we had MobileNet version 2, and then eventually a few years ago we had ELO v8. Now there is ELO v11, which is much better, and then another family is efficiented. So these are different types of models. So our goal was to make all the models workable in the app. So the models should be plug and play. We can switch the models, and we can also replace the models with newer versions. So we wanted to do that. So the design was done such a way that the input image is switched to the model of our choice, and then the output image is shown to the user. And then we can always add new models. Some results here from different sources. On the more technical side, I don't want to get into too details or talk more about the actual ML model performance, but our goal was always real-time performance. As you can see, the servers, they're capable of producing much higher performance. And when we are saying performance, we can measure that using various matrices. But in this case, it is frame per second. So the general idea is human eye would like to see at least 23 frames per second to have the sense of real-time view. 15 frames per second is sort of acceptable. Of course, we have much higher frame rates these days. We wanted to achieve something like that. As you can see, we are seeing average frame per second on server for different models in the range of 21 to the range of 106, which is quite good, and that is expected from the server. And of course, we did not use a very powerful server. It was a desktop machine, and it is also we can also use something more powerful like Amazon Web Service or Google Cloud Services that would produce much higher results. Then the phones itself, as you can see, at the time we tested these apps, it was iPhone 12 and Google Pixel 6. We wanted to have results for both iPhones and Androids. And as you can see, the frame rates varies. For smaller models, for different types of models, we can see the range of 8 frames per second, which is of course not acceptable. But for other cases, we have up to 37 frames per second, which is much better than the lower frame rates. So we can consider that we have real-time performance on the phones. And of course, much larger models, they are not going to work on any of the phones because of various technical constraints. Eventually, they will work the way the phones are improving, but not at that time. So we don't really have that models running on the phone. Then coming back to citizen science, which is, of course, one of the focus of this talk. And citizen science is always useful. It's a special type of crowdsourcing where volunteers or non-experts or interested people would help a scientific project. And most of the cases, the help is done by collecting data or even analyzing data. That is what we want to use for the RipFinder app. So the idea is we need a citizen science platform, and then the participant would collect the data and upload to the platform. Then the researchers, that can be, in this case, either computer scientists or coastal scientists, they can use that for various tasks. For example, training more ML model, or analyzing the data to see what kind of rip currents are present. So we do need a citizen science platform, which is the medium of this crowdsourcing and collaboration. So we have not very extensive citizen science features in RipFinder, but we are improving that. In the early version, on the screen you see on the left, is the easiest way to create a data collection platform, which is using Google Forms and then Google Drive to save the data. And the citizen science user account would be just a Google account where someone would be able to use their Gmail credential to log in and provide data. We are updating that. In this summer, some of my students, they improved the interface, and now it is based on Google Firebase, which is a much better and more secure platform and state of the art. And we will eventually switch completely to this form of data collection. What kind of data we want to collect is the question. So we want to have small video clips, ideally with as much information as possible from the user. So we have this guided way of collecting data where we ask the user what kind of rip current they saw. And also they can provide us feedback about the performance of the ML model. Is it detecting the rip current, or if it is not detecting the rip current, or if it is detecting something else as rip current? All this can be uploaded using the app itself. And we have a limit of size, but we would expect short video clips of 30 seconds or something like that. There is also option of providing open-ended feedback that we can also use for improving the app or getting more insight about the data itself. So the data validation is a very important part of the data collection process, because anyone can upload any data, and that can be RIP current data or something entirely different thing. So we have different types of data validation process in the overall workflow. So the easiest option, without involving the human time or help from the expert, is to use a large model to detect some of the features and make sure they're indeed RIP current data. Uh, Large models, they can run on the server, and we are getting large language model. We are using large language models a lot these days, something like ChatGPT. We do have large vision models based on vision transformers, which you are seeing here. It's just one variation, which is real-time detection transformer. We have much better models now, and that validation can take place in a server, and make sure that we do have at least coastal data. A lot more can be done using these large models, for example, coastline detection, coastal feature detection, but of course, verifying if we do have RIP current data. And then the final validation, that must be done by human experts. We cannot really replace human experts' opinion with a model. That's not cannot be feasible yet. But that takes more time from the human experts. Another option is to use the insight from the contributors. So that's why we have some feedback. So someone can provide more insight about the types of RIP current, or why the RIP current is forming, or maybe there is a structural RIP that is not detected by the ML model, so they can point that out. And we have much less data about the structural RIP currents than the other types. So these are useful information that is provided by the human contributors, and the citizen science platform is making that possible. So the RipFinder app itself is not available on the App Store for downloading, either on the Google Play Store or the iPhone App Store yet, because we are still improving a lot of features, and it is not completely reliable for general users so that they can rely on it. And there can be impact that so if someone cannot detect a RIP current using the app, and then they rely on that information and try to swim or do something, that can have negative results. So we still have the app in the beta testing phase, mostly with expert users. We tried multiple beta testing groups in various places all over the US, and there was one group in the UK, and the participants are mostly students with some knowledge about RIP current detection, researchers, of course, including me, some groups of lifeguards and surfers and others. So we are trying to expand as we improve the app and get more feedback from the beta testers. At some point in the future, we really want to release the app to the public. But of course, after making sure this is reliable for any users. So moving on to the next topic, which is more about the data itself. So early in the talk, I mentioned that we don't have enough data, not nearly enough to generalize the ML models to detect even same type of RIF currents everywhere. We can only collect data from a local venue and then test the app in that venue to make sure that it works for that types of RIF currents. But there might be other variations that we are not aware of. So, as you can see here, probably I'll get questions about this, that it is easier to detect RIP current from a top-down view, like a drone view. This is a good example. So from top-down view, we can see the flash RIP or the sediment flow is easily visible, which is not that easy to detect from the beach level. But still, we do see some sort of sediment flow. Now, it would be easy to collect more data from the top-down view, and then based on that information, we can collect additional data from the beach level. That would be more useful for the app. Collecting that data, the logistic itself is quite challenging. I am going to talk about a few sources that we have used so far for the data collection. One such source, or this is a completely different project with a different paper that was published recently, is called RipScout. So this is also an app-based system that runs with drones for automated data collection. So it's possible to collect this data using drones by flying the drone manually by a pilot with enough knowledge on rip currents. That would require a lot of human participation. We wanted to automate that process using the same type of workflow where our experience is from the top-down view, the model can somewhat reliably detect rip currents based on the sediment flow or the visual signature. So based on that information, if we automate the drone flight and we tell the drone to fly from point A to point B, of course, on a beach on the coastline, then once a rip current is detected, the drone can automate the data collection process. As you can see here, two examples. The first one on the left side, it can change its height or altitude to collect the rip current data from different heights. On the other hand, it can actually do a 360-degree move around the rip current to collect the data from different view, which can, if from a lower altitude, can simulate the rip current detection from a beach level. So this is one way of diversify our data or have more data to teach the models more about the rip current from different angles. Then another source we used a lot is data from network camera. And of course, we are really thankful for all the camera sources we have from the WebCoast network. So WebCoast is a camera network that is created by NOAA and maintained by Secura. And right now, I believe there are more than 30 cameras there. And I think it is expanding with at least more than 50 cameras in the future. So this extensive camera network helped a lot with the data collection process. I have one example here where I had the opportunity to work personally to set up the camera and then use the data in a more closely to use that for the training process, which is in Santa Cruz, the Walton Lighthouse. We have this camera that is currently public for viewing. There are other cameras that can provide very good view of rip currents. So two sources I mentioned so far, the drone itself and the WebGoose. And of course, the citizen science itself is one of the great way of collecting data, but that would require a more organized way to collect the data. And that is another goal of the RipFinder app. That is, of course, right now limited because we don't have the public version of the app. Only contribution of the data we have is from the beta testing users, which is very limited. Finally, I have a few students with interest to expand the capability of the RipFinder. So this is a very experimental project that was done in this summer in a very early stage. It does work, but we are still improving that. So bringing RipFinder app to a VR or augmented reality headset, similar to the Meta Quest 3 or Apple's virtual reality, augmented reality goggles. So instead of using the phone, is it possible to wear the headset and then see the similar information through the augmented reality interface of the AR headset? So that would show the bounding box showing the rip current, and additional information would pop up whenever a rip current is detected. As you can see, this poster and some additional information, local information about rip current is visible to the user. So at this point, it does work. same types of models are used on the headset, and we are using Unity Scientist technology for creating the app, but still very early stage. Just want to mention that this is something that we are working on. So to conclude, the long-term goal for this app was making sure the users get more information about the beach safety, and they can be aware of the rip current, the danger that is presented by that. And then for the expert users, they can use the same app because they already have the knowledge of rip current. They can contribute using the citizen science platform to collect more data that in future can be used to improve the model and make it more generalizable. As we get more data from different areas of US and other part of the world, if we include that data in the training process, the model will get much better and will be able to detect a wider variety of rip currents. Still, that's the long-term goal. And of course, the design consideration and the challenges to run on the smartphone. Ideally, it should be able to run on the smartphone without relying on the server, which is getting better day by day. We have small GPUs on the smartphone that can do much better AI processing. Phone companies, they're bringing their dedicated AI processor on the phone, which is also going to be helpful for our app, even with the current structure, for real-time processing without internet, or with internet if we have very fast internet, and then collect data using the citizen science platform we have integrated in the app. So that was the overview and the technical background about the app itself and some of the features that we have. And thank you everyone for listening to my talk. And then if there is any question, I would be happy to answer that.
Great. Thank you so much for your presentation. This is Cassandra again, everyone from NOAA Library. And we've already had some questions coming in. Our first question, this was asked before, you touched upon it briefly, but I'm going to ask it again just so you can expand upon it if you need to. I noticed that the example images used to train the model are from elevated views. Can it work with images that are beach level?
Thank you very much for the question. This is indeed a very good question and was one of the technical challenges we always wanted to address since the beginning of creating the app. The main reason for using data from the elevated level is the availability. So we always wanted to start with whatever data we have, and we found out that it's easier to collect data from Google satellite sources. That's what we started with, and then eventually we did some field work and collected more data from the field. It's easier to collect data with drones. So yeah, the answer to the question is because we had more data from the elevated level, we started that to create the initial data set and then adding more data from the beach level. And the answer to the question if it is going to work or not. So the ML models, they works based on the visual signature of the rip current. If we have enough training data with the visual signature of the rip current from the beach level, which is sometimes it can be tricky. Our personal experience is it can also be impacted by something like glare from the sun. So if it is too shiny, nothing is visible, then the vision-based model would not work. As long as it is visible with some sort of visual signature, and we have training data that was used to train the model, it will detect the rip current even from the beach level. So the more data we can use to train the model, the more accurate it would be, more generalizable it would be, and it should be able to detect rip current from different angles, even from the beach level, as long as the rip current is visible from the camera of the phone. I hope I answered the question.
Yes, thank you so much for your response. Our next question, when will the app become available to the general public?
Thank you very much. That is also a great question. So there are some limitations with the logistics of making the app available to the general public. Currently, the major limitation is the model itself is not that generalized. So it's easy for the app to miss rip currents if the type of the recurrence is not something we used to train the model. So that has this danger of misleading someone, which we don't want. And since this can be really fatal, like if someone relies on the app and then depending on the information or lack of information, if they make a decision, that can be disastrous. So we don't want that. Even though we have a strong disclaimer with the current version of the app, just to remind the even expert users participating in the beta testing that this is still a research preview. So that's the current status of the app. We are still improving. We are testing that app, which is more extensive in terms of logistics than our current research team we can handle. But at some point, the way the AI, the ML models are improving, we definitely hope to release the app to the public at some point when we are confident enough that it will be able to detect all types of rip currents, or at least enough types of rip currents to guide the user in real life. I hope that answered the question.
Thank you so much. Our next question, are you still looking for stakeholders to test the app?
Thank you very much. Yes, the answer is yes. We are always looking for beta testing teams to test the app in a more controlled environment. The meaning of that is we want to test the app with expert users who will not completely rely on the app. Rather, they will test the capability of the app and then they will provide us some feedback or they will help with the data collection part. So I am always looking for such interested groups or even single users. In fact, in this summer, we contracted with one such group, a group of lifeguards within the US. So yeah, I'll be happy to talk more about that. I believe my contact information will be shared. So happy to talk more.
Our next question, I'm curious how this collaboration started. Could you talk more about who identified this problem to solve, who, like expertise, is involved in the collaboration, and how community members will be engaged for evaluating the app usefulness?
Thank you so much. Yeah, this is a great question. So that would go back a long time, like at least I'd say 7 or 10 years ago, when the idea was mostly uh, came from my advisor back in my UCSC day when I was working on my PhD. So Professor Dr. Alex Pang was my advisor at that time, and he was working with Dr. Gregory Dusek. So the idea mostly came from them, who has more experience in coastal activities. I myself is not that active in the coastal activities like surfing and this kind of stuff. So yeah, the idea came itself from real life users and scientists who has experience in both sides. My expertise is more in the computer science and AI side, where I would like to apply computer vision for various real life problems. So combining all this expertise, what we have now is the current version of the app. But yeah, we are still the team we have working behind this app is started with Dr. Alex Pang and Dr. Gregory Dusek, and eventually I joined the team in the more computer vision and development side, and we are still actively collaborating. And some of our papers, I believe, is shared on the chat. You'll see the authors list of the paper, and that would give you some idea about the actual team working behind the app. And of course, our students, many of our students actively participated in the development and testing of the app. I don't remember the last part of the question. I believe that is more about how the community would involve
Yes,
in the
how the community members will be engaged for evaluating the app's usefulness.
right. So what we want to know is how well the app is working. The app itself is the user interface. We need more feedback about the effectiveness of the ML models. We are constantly training new models as the newer version or newer variety is coming out, and then we are trying to So this is a plug and play type model in the app. So we can always switch older models with newer models, as well as improving the app itself. So we want to get more feedback from the community members about the effectiveness of the ML model with more data that can be uploaded through the app. Of course, you're welcome to contact with us if you have a large data set that you want to give us, and then telling us more about how well it works or how it does not work in cases. So we would always appreciate more feedback from the community member so that we can improve the app.
Our next question we have you considered adding coastal webcams that are mounted on high-rise hotels that are a mix of public and privately available live webcams? These are available in many coastal areas and operate live 24/7.
Thank you so much. This is a great question, although this is a little bit outside of my expertise. Dr. Greg Duce could have better answer. But what I can say is I have a small slide about the WebGoose program, which is a public-facing website, and I believe many such cameras are already listed in that website, which works as the data source for our app. So the app itself can link to such cameras, but the main goal of the app itself is to use the camera on the phone to detect rip currents. And we do have a resource page or resource tab in the app that can list all these resources. And one such resource to provide additional information is the WebGoose website. And I believe the WebGoose team, which I am not part of that team, but they are constantly adding more cameras from different public resources, such as the hotels.
Great. Thank you so much for your response. Greg did say in the chat that we at WebCOOS are actively adding additional webcams across the US with a focus on RIPs in many locations as a follow-up to that question. Thank you. It looks like we've answered everyone's questions about the app. Thank you again, Dr. Khan, for presenting with us today. And thank you, Rebecca, for organizing today's event. Rebecca, do you have any last comments?
Absolutely. I just wanted to again say thank you for everybody who tunes in for these webinars. If there are any topics that you would like to see covered or anything else that you might be interested in learning more about in terms of citizen science, please feel free to let us know. You can email us at citizenscience@noaa.gov. In the meantime, I just wanted to give the utmost thanks to Dr. Khan for presenting, as well as his team members in the chat today for sharing your wealth of information. I personally think it's really interesting to see the role that AI can play with citizen science as well as public safety. Definitely makes me feel a little bit safer being out there on the beach this past summer. That being said, this webinar series is going to be continuing throughout the fall months. We're going to be focusing on different projects that utilize citizen science and AI in collaboration together. So be on the lookout for those seminar updates that come from the library, and we'll be sharing them as well to our community of practice. And that's it for me.
Awesome. Thank you so much. Audience, we hope to see you next month. Thank you for attending and enjoy the rest of your day.